the right-hand rule, we could see that the magnetic force can produce an interesting trajectory for a charged particle moving through a magnetic field. In the previous example, we saw that a charged particle moving in the plane of the board with a magnetic field pointing out of the board will cause that particle to move in a circular path. Now, let's extend that example by a little bit, and let's ask, what if the particle has a velocity not entirely in the plane of the board, but the particle's velocity is angled somehow relative to the magnetic field? So I could imagine breaking the particle's velocity down into a component that is parallel with the magnetic field and a component that is perpendicular to the magnetic field. Now, if the particle's velocity were only perpendicular, so for the moment I am assuming v parallel is 0, we would have the particle's velocity is perpendicular to the magnetic field, so that particle would feel a magnetic force that causes it to move in a circle. This circular motion is just what we talked about in the previous example on the board. Now, if I ignore that for the moment and I say if the particle's velocity is entirely parallel with the direction of the magnetic field, the particle will move in a certain direction, but because the angle between the velocity and the magnetic field is 0, they are parallel with each other, then there will be no magnetic force on the particle, and if there is no force on the particle, there's no acceleration, so the particle will just continue to move with that same velocity forever. Now, in this particular example, we are just combining these two ideas. So I have an upward velocity that is just going to be constant because there's no force pushing it in the vertical direction. And then I have an inward pointing force from v perpendicular that causes the particle to move in a circle. So if I combine an upward motion with circular motion, I get an upward helical motion, or a motion that kind of spirals upward. So the purpose of the slide is not so much to demonstrate this exact trajectory, but to just demonstrate that you can get interesting trajectories from the magnetic force. So let's ask the question, what would the magnetic force look like on a wire that carries current? If you think about it, charges flow in a wire, and that is an electric current. So if charges are moving, well, that is a Q and a V. So it seems reasonable to expect that a current-carrying wire should also feel a magnetic force. So let's suppose here's a wire. Now, in this example, this wire we are going to assume is infinitely long, and this wire is placed in a background magnetic field. So there is a current flowing through this wire. A current is just a collection of charges that are moving, and the charges are moving with some speed. And something else is creating this magnetic field in the background. I'm not telling you what else is creating this background magnetic field. We're just assuming that it is present. So if I have some charges here, and I colored each of these charges in so we could label and track what happens to each of them, all of these charges are moving because the current is flowing, so all of these charges will feel a magnetic force. Now let's suppose in some interval of time t, each charge is going to move a distance L. So in time interval t, the purple charge moves a distance L through the wire. And in an interval time of t, that same interval of time, the green charge has moved that distance L through the wire. And in this interval of time, every charge in the wire has moved a certain distance L. So the order of the charges is still the same. The red charge was in front, and the red charge will remain in front, and so on. So the force on a charge could be written as QVB sine theta. This is the magnetic force equation we talked about previously. Well, this V is really the velocity of the charges, so V could be thought of as being L over T, the distance the charge moves divided by the time it takes the charge to move that far. Now, if I want, I could rearrange the order of my multiplication and division without really losing anything, and I get something that looks like F equals Q over T LB sine theta. And Q over T looks a lot like electrical current. So if you think about it, you could convince yourself that This Q over T is really just which charge moves in a distance L in a certain time interval. Or you could think of it as, imagine you put a cross section right here and you ask how much charge is going to move past this cross section in a time interval delta t. Well, every charge from right here to the purple charge at the start will cross that cross section that we talked about. So the force on a section of wire could be written as ILB sine theta. Now, one thing I want to emphasize here is we originally assumed that this wire is infinitely long. And you might say, well, wait, if the wire is infinitely long, that means L becomes infinity. Doesn't the force on the wire also become infinity? And the answer to that question is yes. When we work through problems like this, though, we won't really consider an infinitely long wire. We'll just ask, what is the force on a section of wire? And the wire presumably could be much, much longer than that, but we're not asking about the force on the entire wire. We're just asking about the force on a section of the wire. Now, from the right-hand rule, we could determine what direction the force on these charges is going to point. Basically, the right-hand rule is the exact same technique as I described in a previous video, where the forearm will point in the direction of motion. Well, direction of the motion of charges, direction of V, is going to be the same as the direction of the current. So my forearm will point in the same direction as which the current is flowing. So my forearm will point down and to the left. Then I will curl my fingers in the direction of the magnetic field. In this case, my fingers need to curl more than 90 degrees. They need to curl more like 135 degrees. And when I raise my thumb is pointing out of the computer screen. So the force on this section of wire is going to be pointing out of the computer screen. Now, I said in the previous slide that the force on a section of wire is the current flowing through that wire multiplied by a magnetic field. Presumably this magnetic field is created by something else. In the picture I have here, very explicitly I drew the magnetic field to be nice and uniform, but this is not necessarily a requirement. What if that something else that creates the magnetic field is a second wire? So let's consider a very long straight wire that carries current I1. So wire number 1 carries current I1, and this current will create magnetic field B1. So here's my I1 from my current carrying wire, and if I use the right-hand rule described in some of the previous slides, the magnetic field B1 will wrap around this wire in a manner kind of like this. So the magnetic field is coming out of the computer screen over here. B1 points into the computer screen over here. Behind the wire, B1 points to the left. In front of the wire, B1 points to the right. So my 4 fingers are wrapping around the wire as my thumb is pointing straight up towards the top of the computer screen. Now, before I place a second wire, let's just take a look at this picture and notice that here I have a parallel line drawn that is always the same distance away from the wire 1, and I look at this and I realize the strength of the magnetic field is going to be the same at every location along this dotted line because you're always the same distance away from the wire. So B mu naught I over 2 pi r, you're always the same distance away from the wire, so you'll always have the same strength of magnetic field. And also at every point along this dotted line, the magnetic field is going to be pointing into the computer screen. So at every location along this dotted line, the magnetic field has the same strength and points into the computer screen. So this dotted line is where I'm going to place my wire carrying current I2. And the question is going to be, what is the force on this second wire? So here is a wire carrying current I2. Now this wire is going to feel a force because we have a current I2 placed in a background magnetic field B1. There will be a force on this wire. So the force on wire 2 is the current flowing through that wire times the background magnetic field. Wire 1 creates the background magnetic field, so wire 1 creates magnetic field B1 times the sine of the angle between them. Now, recall from the previous slide that F is a force on the section of wire I2 in a magnetic field. I is the current carried in the wire. We're interested about the force on wire 2, so I is going to be the current on wire 2, flowing through wire 2. And B is the magnetic field created by something else. Wire 1 creates the magnetic field, so that's why I have a B1 right here. Now, so as I said, in this case, we're talking about the force on wire 2 that carries current I2 due to the magnetic field created by wire 1. So if the wires are separated by a distance d, I could say at the location of wire 2, the strength of the magnetic field created by wire 1 is given by this. Instead of r, for in your denominator, I'm using d because eventually I want to match the equation written in the textbook. But mu naught I over 2 pi r represents the distance from the wire. Here I'm just labeling the distance from the wire as d. And again, I just want to match at the end of the day was written in the textbook, so that's why I changed r to d. The force on a section of wire due to the magnetic field created by the first wire is then going to be I2 times L times B1, where B1, we take this equation and just plug it in right there, times the sine of theta. Now notice that when the wires are parallel, the magnetic field is always going to be perpendicular to the current. The magnetic field in this case, as I said, points into the computer screen. The current I2 flows straight up towards the top of the computer screen. So that means the current flows up, magnetic field points into, the two are orthogonal with each other, or the two are perpendicular. So I get the sine of 90 degrees is just equal to 1. And if I rearrange the order of the terms, I get the force on wire 2 is given as mu naught I1 I2 over 2 pi d times L. So what about the direction of the force on wire number 2? Well, let's look at a picture where both currents are coming out towards us from the computer screen now. So we're just looking at the same picture as on the previous slide, but from a different perspective. I'm asking about the direction of the force on wire 2. So the direction of the force on wire 2, the current is coming out of the computer screen towards me. The magnetic field B1 is pointing straight up towards the top of the computer screen. From the right-hand rule, my forearm is pointing out of the computer screen in this direction of current I2. My forefingers will curl towards the top of the computer screen in the direction of the magnetic field at the location of that wire. And when I raise my thumb is going to be pointing to the left. So that means the force on the wire carrying current I2 is to the left. So the force on wire 2 is going to be pointing towards wire 1. By Newton's third law, equal and opposite forces, I expect wire 1 to feel a force pulling it to the right. So I expect wire 1 to feel a magnetic force created by the magnetic field flowing through wire 2, created by the magnetic field from the current flowing through wire 2 to point to the right. So wires that have currents flowing parallel with each other will attract each other. And the strength of the force with which they attract is given by this equation here. What if the currents are flowing in opposite directions? Well, from the right-hand rule, my forearm is now pointing into the computer screen. If I pivot my wrist, I curl my forefingers up towards the top of the computer screen, and I find my thumb is pointing away from wire 1. And so the force on wire 2 is to the right. And again, by Newton's third law, or if you want, you could work it out very explicitly, you find that the force on wire 1 due to the magnetic field created by wire 2 which is not shown, is going to point to the left. So parallel wires with currents that flow in the same direction will attract each other. Parallel wires with currents that flow in opposite directions will repel each other.